Sorting, searching, and scaling, these are the foundational operations of modern computing. They are the underlying mechanics that dictate whether a software application runs instantly or grinds to a complete halt. So, why do algorithms care so much about sorting data first? It comes down to efficiency. When raw data is chaotic, finding a specific piece of information becomes a massive bottleneck for the system. Computers can only compare a few pieces of data at a time. If a phone book were printed in random order, you would have to read every single line just to find one name. But when that data is sorted, whether alphabetically or numerically, it immediately unlocks lightning-fast processing for every step that follows. What exactly is a bubble sort? And why is it considered the classic beginner algorithm? It serves as the simplest method to introduce the concept of computational loops and data swaps. Think about lining people up by height. The algorithm compares the first two items. If the left item is larger, they swap places. It then moves to the next pair, compares them, and swaps again if necessary. With each pass down the line, the largest items slowly bubble up to the very end of the list. Because bubble sort compares items one by one, its inefficiency scales rapidly. If you double your dataset, you quadruple the sorting time. By the time you reach millions of rows, processing slows to a complete crawl. To handle massive datasets efficiently, we need a different approach. What is a divide and conquer algorithm? Instead of tackling a huge problem all at once, this approach breaks a large dataset down into tiny, highly manageable pieces. Imagine sorting 100 tangled socks. A divide and conquer approach splits them into 4 piles of 25. You sort those smaller piles incredibly fast, then merge them back together. What starts as one overwhelming task quickly becomes dozens of effortless ones. Building on that concept, how does the merge sort algorithm use this specific divide and conquer strategy? Take an unsorted deck of cards. Merge sorts splits the deck in half, then quarters, all the way down to individual cards. Computationally speaking, a single item is already sorted. The algorithm then merges them back together in perfect order. It does this layer by layer, moving from pairs to groups of 4, then 8s, until the entire deck is unified. To compare the two, bubble sort swaps adjacent items, which makes it highly inefficient for large amounts of data. Merge sort, however, divides and merges, allowing it to handle massive scale effortlessly. Now that we understand sorting, how do we retrieve the data? Once data is sorted, how does a linear search actually find specific information? Linear search is essentially a brute force method. The algorithm checks every single item from start to finish until it finds a match. Much like pulling one sock at a time from a laundry basket, it requires zero prior organization, but it is highly time-consuming. On the other hand, what is a binary search and why is it often considered magical? The answer lies in its hyper-efficiency, though it strictly requires the data to be sorted beforehand. Instead of checking items one by one, binary search jumps to the exact middle of the dataset. If you are trying to guess a number between 1 and 100, your first guess is 50. If the target is higher, you instantly eliminate 1 through 50. You throw away half the dataset in a single step, guess 75, and repeat this halving process until the target is found. This brings up an important question. How do data scientists actually measure if an algorithm is fast or slow? They do not use a physical stopwatch because hardware varies too much. A fast, modern computer will always run inefficient code faster than an old machine. Instead, the objective standard is Big O Notation. This is a mathematical concept that measures exactly how running time or memory usage scales as the volume of input data grows toward infinity. For example, O of 1 represents constant time. The algorithm takes the exact same amount of time whether it is processing 5 items or 5 billion, like instantly checking a bank balance. Conversely, O of n is linear time. Having 10 times more data means it takes 10 times longer to process, similar to a line-by-line text file search. So, why is mastering these basic sorting and searching principles so crucial for advanced data science and AI? Because these operations run constantly under the hood. Database indexing, recommendation engines, and complex machine learning training steps all rely heavily on efficient sorting and searching. Poor data organization forces AI models to waste massive amounts of processing power just finding inputs, which leads directly to inflated cloud computing bills and severely degraded performance. Consider this final point. How much invisible computational power perfectly sorted data, and hyper-efficient searching was required in a fraction of a second just to recommend this very explainer to your screen today.